Okay. Hello everyone. I'm Euijoon, and I would like to thank all the organizers for this wonderful workshop and giving me an opportunity to present my recent work about unified perspective on thermodynamic trade-offs. So this work was collaborated with Jongmin in APCTP, Choi-sung in KIAS, and Youngju in Seoul National University. So I begin with introducing thermodynamic trade-offs I want to consider. So thermodynamic trade-offs are inequalities which give tighter bounds on entropy production, which is a key quantity in stochastic thermodynamics. So here tighter means tighter than the second law of the thermodynamics. So there are lots of thermodynamic trade-offs. The one of the most famous trade-off is thermodynamic uncertainty relations, or TUR. So it says that the EP is lower bounded by the ratio between the scale of the mean observer and the variance of that observer. So here, uh, the observer is the non-equilibrium current. There are some applications of these relations. For example, we can drive trade-off among power, efficiency, and constancy of steady-state heat engine. And also we can use TOR to predict how long can subdiffusion persist or from when the superdiffusion can start. Entropic bounds, or EB, is less known than the TOR, but it also gives the lower bound of the EP. Now the denominator of the right-hand side is replaced with a positive number called chi, which is the time accumulation of the short-time diffusion constant. So using the EB, we can investigate the constraints on Onsager matrix coefficients. And also the good thing about the EB is it is a usually tight bound, which means we can make the inequality unequality. So knowing this, we can use the EB to estimate the entropy production. Here is one example where they estimated the EP in RNA unfolding process. The last one I want to introduce is the classical speed limit. This relation is a bit different from former ones, as the bound is written with statistical distance between initial and final distribution. Speed limit is useful when estimating the minimum time or the dissipation to complete a protocol. For example, we can apply this to chemical reaction network, and we can also use this bound to find the minimum dissipation in the bit erasing process, which is also known as Landauer bound. So here my question is, there are many trade-off relations, but what are the relationship between these inequalities? So can we derive one inequality from others? So to answer this question, we developed an extension of the TOR called XTOR. This can be done by including state-dependent observer with the non-equilibrium current in total observer. So I briefly tell you the difference between the current-like and the state-dependent observer. So let's consider three-state model, and this is one stochastic trajectory. The current-like observers count the net number of jumps. For example, the net jump between state 1 and 3 looks like this. On the other hand, state-dependent observers are about residence time. For example, the residence time at state 1 looks like this. So the XTOR again tells us that the EP is lower bounded, but now we have an omega factor here, which consists of derivative of total observers. This looks a little bit complicated, but we can recover many previously known variants of the TOR. Thus, we can consider XTR as a mother form. So actually, the XTR is not a really mathematical expression, but we can use it for an estimator of the AP. As an example, we consider a particle pulled by an optical tweezer. We can use any combination of the observer. Here I choose the displacement and the difference of the position of particle and the optical tweezer. And alpha is the optimization parameter. And using various values of alpha, we can make a tight estimator of the AP. So going back to my question, we can use the XTOR to make a hierarchy among trade-offs. So trivially, we can recover the TOR by raising state-dependent part, but non-trivially, we can also recover the EB by setting the state-dependent part very cleverly. Here I skip the detail, but you can refer to this published paper. Furthermore, we can drive the power efficiency trade-off for heat engines by setting the current to be a heat from the hotter bath. Finally, we can drive the generalized version of the speed limit by setting the observer in a way that it reduces to a statistical distance. This completes the hierarchy. So usually the trade-offs at higher hierarchy is less informative but is universal, and the trade-offs at lower hierarchy is less universal but is more practical. By making connections and completing the hierarchy, we unveil new trade-offs which were not known before. Here we discover a new speed limit which is applicable to inhomogeneous temperature field. So apart from the previous speed limit which uses Wasserstein 2 distance, here we bound the protocol time by Wasserstein 1 distance. So please note that the naive generalization of the previous speed limit would be violated in some cases. To summarize, we construct a hierarchy among various thermodynamic trade-offs where they stem from the extension of the TOR. We find new trade-offs, especially a generalization of the speed limit. And we are now extending our theory to open quantum systems. Okay, this is the end of my presentation. Thank you for listening.
Thank you very much. The first question is in the chat from the Nas.
Okay, the question is the EB same for both overdamped and underdamped scenario? Yes. So you know that the form of the TOR is different for the underdamped Langevin system, but for the EB